Hello, this is Dr. Christy Patton Lukes, a chemical engineering professor at Missouri S&T, and this series of lessons is for process control. Our textbook for this is the Process Dynamics and Control Fourth Edition by Seaborg, Edgar Mellichamp, and Doyle, and published by Wiley. The, in particular, for this material, I'm going to go through a few examples of dynamic modeling, but really read the textbook. It's got great examples. You definitely want to look at those. We are looking at chapter 2, which is theoretical models of chemical processes. And in the last video, we went through the methodical process for creating such a model. In this lesson, we're going to be looking at a heated stirred tank. Now, if you look at the picture here, we have a tank. The liquid level is height H. The tank is stirred to make sure that it's well mixed, so the properties inside the tank are kind of uniform everywhere. There is a heat input that I've designated as Q using that coil for the heating coil. The flow in is flow rate W naught, so we'll call that a mass flow rate, and it's at temperature T naught. And flow out is flow rate W1, mass flow rate, times at temperature T1. So W is mass flow rate. I want to uh, next think about what kinds of simplifying assumptions I'm going to use. And I think that constant properties and constant cross-sectional area will be useful here. Now, cross-sectional area, if you've looked at a tank, probably there's a little bit of, like rounding at the bottom, and so it may not be exactly constant, but dealing with that minutia isn't going to get in the way of me being able to actually come up with a solution and not really contribute much. So assumptions don't mean they have to be perfectly correct, but they are useful and close enough, okay, for the type of model that I'm looking for. Now, I'm doing a mass balance. So mass balance is going to be that I'm going to do accumulation, which is the change in mass inside the tank. And that's equal to what comes in minus what comes out plus what is generated. In this case, there is no reaction, so just in minus out. If I recast this using our variables, then the mass in the tank is density times volume. Volume is A times H. So I'm looking at the change in density times A times H with respect to time. And flow rate in is W naught, flow rate out is W1. And I can further simplify this derivative by noting that rho and A are constant, so it is rho A dH dt equals W naught minus W1. I also can do an energy balance, and if I neglect kinetic and potential energy, then an energy balance will be for the system that the energy contained and changing is going to be internal energy. So du dt is the change in the energy that flows in and out. That's my enthalpy times those flow rates. And then any heat transfer that is added into the system from my heating coil. In this case, I've got a negative delta because it's in minus out instead of out minus in. And then I have U is defined because this is the total internal energy, is the integral of mass times CV dt. And the specific enthalpy is the integral of Cp dt. Now, each of these will be integrated from some starting point, so Tref, reference, okay, up to the temperature that's appropriate. If I combine these things, then my energy balance becomes, so the change in U, I need the mass, so rho AH. Rho and A are constant, so they're out of the derivative, H is inside. And for the U, the specific U, it's CV dt. And if I assume constant Cp, then I'm also assuming constant Cv. All right, so I end up with rho ACV outside, derivative of H times T dt. And then my flow in is W naught. It carries energy Cp T naught minus T ref. And then minus what flows out, W1, C sub P, T1 minus T ref. And then add in our heat transfer that we don't really know what it is. Now I can apply a product rule to this. So the derivative of H times T with respect to time is T times dH dt plus H times dt dt. All right, so that's pretty much my balance here. Now, what about analyzing this about my variables? I have two variables that are changing, and then I have other variables. Well, some of them are constant. So rho A CV, which is approximately CP, we can deal with that later. Those are constant. But then I have W naught, I have T naught, I have W1, and I have Q that are additional variables. Now T ref, I guess, is also a constant. So because it's an arbitrary choice I make for my reference temperature. And now that I've done this, I see that I have W naught, W1, Q, T naught as all my other variables. And so my thought process now should be, are these disturbances or are they manipulated? So perhaps T naught and those flow rates are going to come in and I have very little control. If I change this, it will most directly affect the height in the tank. And if I change this, I can compensate for those changes with Q. Okay, so maybe W naught and Q are going to be treated as disturbances. W1 and T naught are going to be more manipulated variables. But again, this portion is going to be a little better determined once we know more about our system and our goals. This concludes this video lesson, an example on a heated stirred tank. We'll look at other examples in other videos. Thank you very much.